Hi, this is Theorem. Today we're going to be discussing sequences. We'll start with defining a sequence. One way to define a sequence is by saying an equals f of n, and this gives us the general term of a sequence. Okay? The number in the subscript is called the index. Generally, the index starts at 1 and continues through the positive integers. For example, we could define an equals n squared. This is a formula for the terms of the sequence given the index. So the first few terms are 1, because you plug in n equals 1, and n squared is given by 1. When you plug in n equals 2, n squared is given by 4. When you plug in n equals 3, n squared is given by 9, etc. Okay, similarly, if we define the general term an equals minus 1 to the n times 2 to the minus n, the first few terms are minus 1/2, which is what you get when you plug in n equals 1 to the formula, then 1/4, that's positive, and that's what you get when you plug in n equals 2. Similarly, n equals 3 gives minus 1/8, and n equals 4 gives 1/16. But these are kind of more straightforward definitions of formulas for the general term, but you could be as creative as you want with this. You could define a sub n to be equal to the number of letters in the word for n in English. And then the first few terms of that sequence would be 3, because this is the number of letters in 1, 3, because that's the number of letters in 2, 5, because that's the number of letters in 3, etc. Okay, and you could have a lot of fun examples of sequences. There's a whole website devoted to interesting sequences throughout mathematics. It's called oeis.org. That's the online encyclopedia of integer sequences, and definitely feel free to explore that. Another way to define a sequence is by giving a list of initial terms and then trying to guess the general term from those first few. And when you're trying to do this, one good way to get a hint of what the correct general term is by looking at the differences and ratios between terms. So let's look at a couple of examples. The first example here is 1/3, 4/5, 9/7, 16/9, 25/11, etc. So when I look at this, I notice that the numerators are very familiar. These are the, these are the squares. Okay. As for the denominators, these are, well, looking at the differences, you're adding 2 between each term. So, and indeed, these are all odd numbers. So if I want a formula for the general term, I'm going to put the appropriate square in the numerator, and in the denominator, I'm going to put a formula for odd numbers starting with 3, and that would be given by 2n plus 1. Because when I plug in n equals 1, I get 3. And then plugging in n equals 2 gives 5, etc. Okay, let's look at number 2. We have 2, 5, 9, 14, 20, etc. So looking at the difference between these, it goes first plus 3, then plus 4, then plus 5, then plus 6. So this is a giveaway for a quadratic function. When you have differences that are steadily increasing in a linear way, that tells us we're looking at a quadratic function of n. So what's left for us to figure out is what is that quadratic function of n. So it's going to look something like an squared plus bn plus c. And we know that when we plug in n equals 1, we get 2. So that'll be a plus b plus c equals 2. When I plug in n equals 2, I get 5. So 4a plus 2b plus c equals 5. And similarly, when I plug in n equals 3, I get 9, which tells me 9a plus 3b plus c equals 9. So let's try and figure out what a, b, and c are based on this. Well, one way to do this is to combine equations. I think that's what we'll do. We're going to take minus the first two equations. Actually, let's subtract the first equation from the second equation. We'll get, and we can kind of follow this down here. We'll get 3a plus b equals 3. And then we can subtract the second equation from the third equation to get 5a plus b equals 4. Okay, doing this one more time, we get, subtracting the first equation from the second equation, we get 2a equals 1. This tells us that a equals a half, okay, which tells us in turn that b is equal to 3 halves. And plugging that into the first equation, we get that c is equal to 0. Okay. So putting that all together, this will be general term a sub n will be given by 1/2 n squared plus 3/2 n, or n times n plus 3 divided by 2. Okay, I'm going to circle this here. Took a bit more work than the first example, but the key was knowing what type of function to look for. Okay, and this was the answer for our first example. Okay, as for the third example, this one is a bit easier to figure out because the only thing that changes between terms is this denominator. Oh, I'm sorry, we have not only the denominator, but these functions also change. So we can give a piecewise definition of this function. We'll write a sub n equals sine pi over n. Let's make it pi over n plus 1 when n is odd, and cosine pi over n plus 1 when n is even. Okay, and sometimes these piecewise definitions, meaning you give different values for the function depending on what the n is, sometimes that's the best you can do. Okay. Another way to define a sequence is using a recurrence relation. And what that means is that the sequence is given by stating the initial terms, maybe just the first or maybe multiple initial terms, and then a recipe for constructing the next term. For example, the Fibonacci sequence, this is a famous sequence. We start with a1 equals 1 and a2 equals 1. And then an equals an minus 1 plus an minus 2 for n greater than or equal to 3. Okay, so if we wanted to compile some of the terms of the sequence, well, we know the first two are 1. Then to get the next one, you add these two together. And that gives you 2. To get the next one, you add these two together, which gives you 3. And in a similar way, you get all the terms of the sequence. Okay. Here's another example. If you let a1 equals 1, and you take a sub n to be the sum of all terms from a1 to an minus 1. Or another way of writing that would be an equals the sum from I equals 1 to n minus 1 of a sub I. So let's draw the chart this way. Might be a bit neater. Okay, so we know that the first term is 1. The second term will be the sum of all of the terms from 1 to 1, which is just 1 itself. So that's 1. The third term will be the sum of all of the previous ones. That's 2. The fourth term will be the sum of all the previous, which gives us 4. The fifth one will be the sum of all the previous, which is 8. And you might see a pattern here. Okay. In the end, another way to write this, we should make sure that this is correct, is a sub n equals 2 to the n minus 2 for all n greater than or equal to 2. Okay, and a sub 1 equals 1. Okay, so that's a general term for this sequence, which we initially defined in terms of a recurrence relation. Okay, now we have a sense of what a sequence is, but what is a limit? Okay, here's a formal definition of a limit, and if it sounds a little bit like Greek, that's okay. A sequence has the limit L, a sequence an has the limit L, and this idea is also written as limit as n goes to infinity of a sub n equals L, or an approaches L as n approaches infinity, if for any epsilon greater than 0, you can think of that as a small number, there exists an n, capital N greater than 0, such that for all little n greater than capital N, a sub little n minus L, absolute value, is less than epsilon. In other words, for n sufficiently large, all terms a sub n will be within epsilon of L. So as you move along your sequence, getting closer and closer to your limit. If a sequence has a limit, it converges or is convergent. If it does not have a limit, then it diverges or is divergent. Okay, now let's discuss this concept of a limit a bit more informally, because that definition can be a bit difficult to digest. And with apologies to Randall Munroe, we're going to borrow the format of an XKCD comic. So we have a conversation between two people here. The first says, the limit of 1 over n as n goes to infinity is 0. He points to this graph. See, it gets smaller and smaller. Then the skeptic responds, those are just 5 values. Maybe it'll get bigger. Right now it's getting smaller, but maybe sometimes down the line it'll get bigger. Do you know that it always stays small? He responds, well, how small do you want it? The skeptic says, really small, less than a millionth. He responds, okay, then just wait until n is bigger than a million. After that, by algebra, 1 over n is always less than a millionth. The skeptic responds, that is persuasive, but maybe I didn't go small enough. Okay, he chose a millionth, but just because I'm smaller than a millionth doesn't mean that I'm so small that I'm getting pressed up against 0. There's lots of numbers less than a millionth. Okay, so our initial mathematician replies, how about this? No matter what tiny number epsilon you pick, I can find an n that works. The skeptic replies, I'm listening. The mathematician says, if epsilon is tiny, then 1 over epsilon is big. Take n to be some integer, at least as big as that. The skeptic replies, so if epsilon is 1 over a trillion, then n could be a trillion or bigger. The mathematician replies, exactly. If you wait until a trillion or more, then all the terms in the sequence afterwards will be less than a trillionth. You can do that for any epsilon, no matter how small. You're always going to be able to find an n so that everything after that n is smaller than that epsilon. So the sequence really does approach 0. The skeptic replies, okay, I'm convinced, but I still don't like you. That's my informal interpretation of the definition of a limit. It's really kind of a conversation between a person who wants to see it get really close to that limit and the mathematician saying, here's how I can get you close to that, as close as you want to that limit by moving further down the sequence. Okay, now we have an intuition perhaps for what a limit is, but let's look now at how to compute limits. Okay, so one way to compute a limit is when we're looking at functions of continuous variables. If the limit as x approaches infinity of f of x is equal to L, okay, so that's a function of a continuous variable f, and we know how to compute limits of functions of continuous variables. And f of n is an, so our sequence is defined in terms of that continuous function. When n is an integer, it's just the integer values of that function, then the limit as n goes to infinity of a sub n equals L. Okay, so the idea here is, let's say you have your x-axis, and here's your function f of x, and it eventually approaches a limit. What we're saying is, let's say you just take the integer values of this, and that's your sequence. Okay, so this is, a sub 1, well, or rather, this is 1, 2, 3, 4, etc. This is the value here is a sub 1. This value is a sub 2, etc. Okay, so then taking the limit of the whole function will give you the limit of this sequence of red points. And because we're computing limits of functions of continuous variables, L'Hopital's rule may come in handy here. But you can never use L'Hopital's rule directly on a sequence because it's specifically related to functions to differentiable functions. Okay, so let's look at this first example. We have a sub n equals 1 over n to the r for some positive number r. Well, I know how to compute the limit as x goes to infinity of 1 over x to the r, right? Because if r is a positive number, x to the r becomes arbitrarily large. And if you take 1 over an arbitrarily large number, you'll get 0. Okay, well, since we're looking at the values of this function at the integers, the limit as n goes to infinity, so this implies the limit as n goes to infinity of 1 over n to the r is also equal to 0. Okay, and we're deducing that fact about this sequence from the fact about the function. Okay, how about a sub n equals n over 2 to the n? So here again, we're going to compute a limit as x goes to infinity of x over 2 to the x. Okay, again, we're looking at values of a function. Okay, and this we can see as an indeterminate form. Both the numerator and the denominator approach infinity. So by L'Hopital's rule, we can take the derivative of the top and the bottom and compute the limit of that ratio. What we obtain is 1 over 2 to the x ln 2. And as we can see, the top is now constant and the bottom is still going off to infinity. So this limit also equals 0. Okay, so that's a fact about this continuous function. But as we pointed out before, this implies that the limit of the sequence is also 0. Okay? And here's a bunch of limit laws that you can find also in the section in Stewart. He goes through all of these. Suppose an and bn are convergent sequences with the limit as n approaches infinity of a sub n equals a, capital A, and limit as n approaches infinity of b sub n equals capital B, and c is a constant. Then the limit of an plus bn equals the sum of the limits a plus b. The limit as a sub n minus b sub n is equal to the difference of the limits, a minus b. Okay, if I multiply every term of the sequence by a constant, so limit as n approaches infinity of c a sub n, then that's the same as just multiplying the limit by that constant. So I get ca. Okay. If you have a sequence which is always constant, it takes the same value at every step, then its limit is just itself. Excuse me. If you're taking the limit of a sub n times b sub n, then that's also the product of the limits, a times b. If you're taking a limit of quotients, an over bn, then that's going to be a over b, but here you have the important condition that b must not be equal to 0. If it is, then you can't divide by it, obviously. If the limit as n approaches, if you're trying to compute a pth power, where p is some positive number, and you also have the condition that all terms of the sequence an are positive, then the limit of a sub n to the p is equal to a to the p. Okay, you can just apply the power to the limit. It's the same as the limit of the sequence raised to that power. Okay, so there are a lot of things that you can do to each term of the sequence, and then when you apply the limit, it's as if you just have to apply that function to the limit. Okay. Furthermore, if f of x is continuous at a, it's a function which is continuous at the limit of the sequence a sub n, then the limit of f of a sub n equals f of the limit, which is f of a. Okay, it's a lot to digest. I suggest using this or the corresponding table in the book as reference, but we're just going to try and get some practice with it, and hopefully with practice, they'll become more intuitive. So let's compute the following limits. We're asked to compute limit as n approaches infinity of 1 plus the square root of arctangent of n. Okay. Well, the first thing that I know, if we can assume that both of the sum ends are convergent, then this will be equal to limit as n goes to infinity of 1 plus limit as n goes to infinity of square root of arctan of n. Okay, and this does assume, I'm going to put a star here, assumes everything converges. Okay, a lot of messy things can happen if you try to apply the limit laws when the component sequences don't actually converge. So let's assume for now that everything converges, and we'll see later if that's justified. Okay, so then this, well, we know that the limit of a constant sequence is just the constant, so that's 1, plus, now we have the limit of a square root. So square root is a continuous function for all non-negative numbers, right? So, or for all, its behavior at 0 is a little tricky. If it's approaching from the positive numbers, it's continuous up to and including 0. But obviously it can't go past 0 because then you're taking square root of negative numbers. So let's pass the limit inside of the square root, assuming that the limit of the inside here is convergent to a positive number. So let's do that. And we'll put a star here. Obviously, this only works if you're convergent. Okay. Well, what about the limit of arctangent of n? So let's recall, note, limit as x goes to infinity of arctangent of x, that's pi over 2. Okay, and that's something that you can refer to and when we started learning about trigonometric functions. But using that fact, you can infer the same thing for the sequence, which is just the integer values of this function. So that gives us 1 plus the square root of pi over 2. The fact that this converged to a positive number tells us that we were entitled to do this limit trick passing inside of the square root, and that in turn tells us that that we were allowed to break up the sum this way. Okay. So all of these stars were justified, though you should be careful. If you're ever breaking down a sequence like this and you run into a divergent sequence somewhere in there, then you have to go back to the beginning. But using the limit laws from the previous page, including the passing inside of a continuous function like the square root, as well as a sum of sequences, as well as the function of continuous variable rule that we saw earlier, using all of those together, we were able to deduce this limit. Okay, now let's do one more. So we're taking the limit as n approaches infinity of 2 times cosine pi over n. This is 2 times limit of cosine, and as n goes to infinity, of cosine of pi over n. Okay, again, this requires that this sequence actually converges. Okay. Now, taking the limit of a cosine, because the cosine is continuous everywhere for all real numbers, then assuming that the inside converges, we can pass the limit inside of the cosine. So we'll take 2 times cosine of the limit as n goes to infinity of pi over n. Again, there's an assumption here that everything converges. And indeed, pi over n, you could interpret this as the integer points of the function pi over x. As x goes to infinity, that goes to 0. So too, this sequence converges to 0. Okay, which justifies the asterisks that we used here. And we know that the cosine of 0 is 1, so the answer here is 2. Okay, so it can be a little tricky at first, and if you want to be thoroughly rigorous, you're going to have to use some of these asterisks and make sure to double check your work. But most of the time, just following your intuition and making sure that and kind of putting limits inside of functions and stuff, it usually works out. So only in rare circumstances are these asterisks, will you need to follow up on these asterisks in problems that will be assigned in this course. Okay, here's one more theorem about sequence convergence. Suppose there are three sequences, an, bn, and cn, that always satisfy the inequality an is less than or equal to bn, which is less than or equal to cn, for all n. Then if an and cn both converge to L, then so does bn. And this is called the squeeze theorem, because if you have something like this and something like this, and they're both approaching the same limit, then anything in the middle is going to get squeezed to that limit as well. Okay? And that's why it's called the squeeze theorem. One consequence of the squeeze theorem is that if the absolute value of a sub n approaches 0 as n goes to infinity, then a sub n, without the absolute values, also goes to 0. Why is this? It's an application of the squeeze theorem, because minus the absolute value is less than or equal to a sub n, which is less than or equal to positive the absolute value of a sub n, and the outer two converge to 0. We know that a sub n converges to 0, the absolute value, so just by using the limit laws, minus the absolute value of a sub n also converges to 0. So since those outer two converge to 0, the inner sequence is squeezed to 0 as well. Okay. One final topic for this lecture is the monotonic sequence theorem. First, we need to define increasing, decreasing, and monotonic sequences. A sequence an is increasing if an plus 1 is greater than an for all n greater than or equal to 1. Okay, that means you're stepping up with each term of the sequence. For example, 1, 2, 3, 4, 5, etc. Because 2 is greater than 1, 3 is greater than 2, etc. It's an increasing sequence. A sequence an is decreasing if a sub n plus 1 is less than a sub n for all n greater than or equal to 1. For example, a half, a third, a quarter, a fifth, etc. Because a third is less than a half and a quarter is less than a third, and every step of the sequence you're stepping down, it's called decreasing. A sequence is monotonic if it is either increasing or decreasing. Okay, so a sequence that is not monotonic is one that goes in both directions. Maybe for the first two terms it goes up, but then it goes down, maybe it goes up again, etc. It doesn't go in a single direction. Now we'll define a bounded sequence. A sequence an is bounded above if there is a number capital M such that a sub n is less than or equal to capital M for all n greater than or equal to 1. So all terms of the sequence are below this capital M. A sequence an is bounded below if there is a number m, little m, such that a sub n is greater than or equal to little m for all n greater than or equal to 1. All terms of the sequence are above little m. A sequence is bounded if it is bounded above and below. So if I'm graphing all the terms of the sequence, I'm going to be able to find a capital M and a little m, so that all terms of the sequence are between these two horizontal lines. Okay. Now we can state the monotonic sequence theorem, since we've defined all of the relevant terms. The theorem says every bounded monotonic sequence converges. Okay. That's a pretty powerful statement. And the idea of the proof of this statement is that, and the proof is pretty much the same whether it's increasing or decreasing. So we'll suppose the sequence is increasing. You find the smallest number, which is above all terms of the sequence. Okay, and you know that the sequence is bounded, so some number exists, so just find the smallest one. And since that's smallest, the sequence has to get arbitrarily close to that smallest number. And that's how you know that it converges. Okay, now let's look at an example of an application of the monotonic sequence theorem. Consider the sequence a sub n equals 1 minus 1 over n. Okay, so the first term of that sequence is 0, because it's 1 minus 1 over 1. And then it's a half. And then it's 2/3, 3/4, etc. So we know that this sequence is bounded above by 1, since we're always subtracting a positive number. 1 over n is always positive, so this is always bounded above by 1. We know also that it's bounded below by 0, since we know 1 over n is always less than or equal to 1. And so when you subtract 1 minus 1 over n, then it's going to be greater than or equal to 0. That means that it's bounded, right? Bounded above and bounded below means bounded. We also know that it's monotonic increasing, since we subtract smaller and smaller numbers. 1 minus 1/2 is going to be greater than is going to be less than 1 minus 1/3, which is less than 1 minus 1/4, etc. You're always getting bigger because the numbers you subtract from 1 are always getting smaller. So putting together the facts that the sequence is bounded and that it's monotonic increasing tells us that the sequence converges. We could have also figured this out in a different way. We could have just said the limit as n goes to infinity, 1 minus 1 over n, apply a limit law, and get the limit as n goes to infinity of 1 minus limit as n goes to infinity of 1 over n. And then using results we've deduced already, you would get that this is 1 minus 0, which is 1. So that would be an alternative way to compute the limit. But even without knowing the precise limit, I can be certain that the sequence converges based on the monotonic sequence theorem. Okay, and there are cases where you aren't able to compute a limit, but the monotonic sequence theorem tells us that a limit does in fact exist, even if we can't compute it. Okay, we're going to finish the lecture there. Thank you so much for your attention. Have a great day.